Hello, everyone. So today we're going to be wrapping up chapter 2 by talking about the temperature dependence of chemical reactions. So what we're doing today is really kind of coupling together what we've uh, learned last time about the enthalpies of reaction and adding in what we've learned previously about how enthalpies are both temperature and pressure dependent. And this is really important because it turns out that most chemical reactions we care about don't tend to occur at standard temperature or pressure. And so our way of adjusting for this is essentially going to be trying to correct for the enthalpies of both the products and the reactants independently, and then essentially adding them into our classic enthalpy of reaction equation, where say I have a new set of temperature conditions. I can go ahead and adjust the enthalpy uh, of my products and my reactants for this new temperature independently. We can do something very similar for pressures, but it turns out for an ideal gas, well, I don't need to because my Joule-Thomson coefficient is 0. And then if I am going to adjust my enthalpies for pressure, I will need a Joule-Thomson coefficient to essentially complete the process. However, let's go ahead and focus on the easier case of temperatures. So let's say I want to try and adjust my new enthalpy of reaction to a temperature 2, and I already know it at, say, temperature 1. Well, we can do this by adjusting my product and reactant enthalpy independently, because I know that my product's enthalpy is going to change based on temperature by the heat capacity. Now, again, we're assuming relatively small temperature differences where I'm able to use just the simple linear heat capacity and I don't have to use the full Shamati equation. Though watch out, occasionally you will need to make use of a linear expanded version of the heat capacity for large temperature differences. And so we can go ahead and do this for both our products and our reactants independently. And then we can go ahead and play a little bit shuffle with terms. We can first collect my differences in enthalpies up front, and then our differences in heat capacities out back. Where again, what we're going to see is its enthalpy of products minus reactants and heat capacities of products minus reactants, where it can then factor out my change in temperature. And this reduces down to a fairly simple equation, that my enthalpy of reaction at my new temp is just the enthalpy of reaction at my old temp plus the differences in the heat capacities of my products minus reactants times the difference in temperature. Now, one of the things that you should watch out for is the fact that this difference in heat capacities should account for any stoichiometric coefficients, just like we did when evaluating our enthalpy differences originally. Now, this equation is essentially called Kirchhoff's law, and it's worth noting that it tends to hold best at relatively minor temperature differences of less than 100 degrees. As soon as the temperature differences start becoming greater than 100 degrees, then the non-linearity in our heat capacities really start kicking in. And so you'll need to essentially take the differences of more of a Shamati or expanded version of our heat capacities. But instead, this is often done using modern tables or sets of literature values. However, it is worth noting that typically we tend to see the heat capacities, the enthalpies of each individual species being a little bit more sensitive to temperature differences than 100 degrees. And one of the reasons why is for most chemical reactions, the heat capacities of the products and the reactants are relatively similar. And so a lot of the difference ends up canceling out. However, it is worth noting that when you see a lot of phase changes or one solid breaking up into several gases, you may actually start to see the difference in heat capacities becoming of the same magnitude or very occasionally greater than the individual heat capacities themselves. So the Kirchhoff's law is actually a fairly simple rule of thumb we can use to evaluate the temperature differences of a lot of different chemical reactions. So let's go ahead and try and apply it for one of the classic physical reactions out there, and that's just simply the melting of ice, going from solid water to liquid water. Now, one of the problems we often end up finding is that this reaction is listed under standard conditions, 25 degrees C. It turns out ice doesn't typically melt at 25 degrees C because it already happened at 0. So in order to find the enthalpy difference under these two conditions, we're going to need to make use of Kirchhoff's law. However, I want to actually kind of illustrate how we can look at this reaction a little bit more visually than the simple mathematic expression we derived on the last slide. So the reaction we're interested in is going from solid water to liquid water at 0 degrees. However, the reaction or conditions we really have is going from solid to liquid at 25 degrees C. So I'm going to need to make use of temperature corrections. And so we know that these temperature corrections can be given as the heat capacity times the difference in temperature for each set of conditions. So what I can do is make use of this thermodynamic cycle and the fact that if I start at one place and go to a second place, the path or the value difference doesn't depend on which path I take. So it turns out that the enthalpy of reaction at 0 is going to be the same thing as taking the negative of this path, because I'm essentially taking this heat capacity times the difference in temperature and going backwards, plus my enthalpy of reaction, plus my heating of the liquid, or in this case, the cooling. And this essentially breaks down to our original Kirchhoff's law of the enthalpy of reaction at 25 degrees plus the difference in heat capacities times the change in temperature. So we can go ahead and crank in these numerical values. So I'll have the enthalpy of my product minus the enthalpy of my reactant, where we have a nice sign cancellation, plus the difference in my two heat capacities, solid product minus reactant, and then times the difference in temperature, which is a decrease of 25 degrees C. And when we do this, what we find is that the enthalpy of reaction at standard temp for melting ice is 6 kilojoules per mole, but it ends up being almost a full kilojoule lower at the melting point of ice. So it is actually worth noting that we have a fairly significant difference in between these two temperature regimes. So this is one of the reasons why making use of Kirchhoff's law can actually be fairly important. Otherwise, you might be, say, 20% off on your enthalpy of reaction, which quickly mounts up to being a fairly significant value. Now, one of the other reasons why it's often useful to, say, look at these thermodynamic cycles is because they'll also help you describe things that the simple Kirchhoff's law itself might not always be able to describe. So we can use these same ideas if I'm trying to figure out how much heat it takes to, say, turn negative 20 degree ice to 20 degree water. So essentially I have ice outside on a very cold day, and I want to try and make it into water that won't actually freeze my hands. So in this case, we're going to notice a slight difference in our set of values, because now my enthalpy of reaction isn't just a single temperature. It's actually evaluating both a temperature change and a chemical change. And it's very important to be able to describe these multi-part systems when dealing with real reactions and real systems. So we can essentially evaluate this by taking, for my new enthalpy of reaction, by taking the heat capacity of my solid times my temperature difference for the first step, plus the enthalpy of reaction, plus the heat capacity and the temperature difference for the second step. So for the first step, I'm essentially warming up the ice 45 degrees. And then I have my chemical reaction, and then I'm cooling down my water by 5 degrees. So one of the things that's worth noting is that none of these individual steps is actually happening. In truth, I'm probably warming up to 0, melting, and then warming up some more. But this is one of the useful things about thermodynamic cycles. The path doesn't matter. As long as you have the numbers for a path, you get the right description. And so what we end up finding under this case is that my enthalpy of reaction is 7.3 kilojoules. So this is over 2 kilojoules higher than just, say, going from just melting 0 degree water, and it's a full 1.3 kilojoules higher than melting ice at 25 degrees C. And essentially, the difference in between these values comes from I had to spend a significant amount of energy just warming up the ice and then the water. And so again, this is one of the important things when trying to describe real chemical systems, is we often need to account for multiple changes, even for a simple process. That you need to be able to account for what chemical reactions have occurred, as well as any sort of temperature changes, and also realize that the conditions that you often have thermodynamic values for may not be the conditions that you're actually operating at, and you need to be able to change them at will. So that brings us pretty much to the end of enthalpy and internal energy. However, we'll still see it again as we start up next time on entropy. Till then, take care.